All right, this is AP Statistics B, Unit 3, Lesson 5, Errors in Hypothesis Testing. So we're going to see if we can figure out the error of a type, the probability of a type 1 and a type 2 error. So here's the problem. The mean of a population is believed to be 40. So the mean is 40. At least it's believed to be so. With a standard deviation of 4. So sigma is 4. A sample size of 25 is taken. At the 5% significance level, alpha is 0.05. Calculate the probability of a type 1 error. Probability of type 1 is the probability of a false positive. It's the probability that you reject the null and say there is a real difference, that it's not actually 40, but that it's greater than 40 or less. We're saying less, let's say less than 40 for a type 1. Okay? Probably, so we say it actually is less when it really isn't. So the probability of type 1 is actually just alpha. So here's the geometry that says it here. Okay, so alpha, when we say the alternative hypothesis is that mu is less than 40, is the area in the tail. It's just alpha. Okay, for a two-tailed test, it would still be alpha because the area of both tails is considered. So it is alpha, it is 0.05. Okay, it's a little more complicated when we need to find the probability of a type 2 error. Okay, so here's what I'm going to do. I need to calculate a z-score at which I would reject or fail to reject. So the type 2 error is when you fail to reject the null. When you say there is no real difference, that the difference is just statistical variation. But there actually is. So it's a false negative. It's like saying you don't have cancer when you really do. All right? Type 1 error is saying you do have cancer when you really don't, a false positive. Okay? So we fail to reject the null. And when would we fail to reject the null? Well, let's look at that here. We'd fail to reject the null for anything in this region here. Anything in this region right there. We'd fail to reject the null. We'd say there is no evidence that there actually is a real difference, that any difference you see is statistical variation. Okay, that's the chance, the z-scores that would result in that. So we need to calculate a z-score here. All right, so z, let's figure out z. Z is the mean. Actually, the z-score for an alpha, left tail alpha is 0.5. So we're going to do inverse CDF, or inverse norm. Inverse CDF. I believe that's the formula here. At 0.05. Okay. Inverse CDF at 0.05. All right, let's go ahead and bring up Desmos here. Oh, don't have it open, so open Desmos. Okay, inverse CDF. And that's inverse CDF is the function in Desmos. All right, and I want to figure out a z-score for 0.05. Oh, I need to specify a distribution, normal dist. And then if I leave it blank, it's mean of 0, standard deviation of 1. 0.05. Okay? And I'm going to call that z. Okay? So negative 1.645. Okay? So this value is negative 1.645. Okay? Which corresponds to what real score in this particular case? That's the trick. We need to, because this is a normal distribution with a mean of 0 and a standard deviation of 1. What real score does that correspond to? What x score, right? What difference here? So let's do it this way. X bar, or x equals x bar minus mu divided by standard deviation divided by the square root of n, right? And if I solve for x bar, what x bar value will that give? That gives me the z-score. And actually I need to label this z, not x. Okay. Z, there we go. All right, so I'm going to solve for z, or solve for x. X, or z times sigma divided by square root n equals x bar minus mu. X bar is mu plus sigma divided by square root n z. Okay? So let's figure out what x bar is. X bar is mu 40 plus the standard deviation, which is, standard deviation is 4, divided by the square root of n, square root of 25, times my z-score, 1.645. Okay? And x bar is approximately, let's go to our calculator here. Okay, I've already got z here as negative 1.645. So 40 plus 4 divided square root 25 times, I can type in the value, but it's more accurate just to use z. So 38.68. Okay, so that corresponds to an x bar of 38.68. Okay, 38.68. Now, what if the actual mean, so at 38.68, as if I get a z-score less than 38 points, or raw score, the raw mean less than 38.68, I will reject the null and say there's a real difference. Okay, if it's greater than 38.68, I will fail to reject. Okay. All right. Now, what if it says the actual mean is 39? The actual mean is 39. What is the probability that I will reject falsely? Okay. So 39 is a little higher than that. Okay. And we're going to say the mean is actually 39. So we've got this offset. We've got the peak of the normal curve right here at 39. Okay. And so what I'm after here is the probability under this curve that I get a score in this range. So I'm going to get a raw score of 38.68 or higher. And what is the area under the curve in that range? This is actually going to be quite high because there's not much real difference here. Okay. All right. So that's the probability of a type 2 error. Okay. Well, let's go ahead and find that. So we're going to calculate the area under the curve if the mean is 38. So the mean is 38. So z is 38. Actually, x bar minus 30, actually, yeah. 38.68. 38.68 minus the actual now, which is 39, divided by same sigma and same standard deviation. So it's 4 divided square root 25. So this z-score is boom, 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 boom. 38.68 minus 39, all divided by 4 divided by square root 25. Okay, so that's a z-score of negative 0.4. Okay, now I need to calculate the area to the right of that. So here we go, normal dist. Okay, just 0 and 1. And what is the probability that I get a score that high or higher? Cumulative probability, so from negative 0.4 okay, yeah, negative 0.4 to infinity. And I get 65.5%. Okay. So that's the probability of a type 2 error and the reason the probability of a type 2 error is so high is there is very little difference between what I assumed it was and what it actually was. So the chance that I'm going to get it wrong, 39, is quite high if the real difference is very little. Now, if the difference is greater, then the probability becomes less. So for example, let's say we had a normal distribution centered on 40, and let's say we chose, or we were testing the probability of a type 2 with a 30. Okay, in which case the area at the cutoff that I found from the 40, which is maybe right here, that z-score corresponds to a area under the green curve right over here. So the further apart the assumed mean and the actual mean, the less the chance there is of getting it wrong. That makes a lot of sense, actually.